Jnanam paramam dheyam. Knowledge is supreme.
So, next we have assumed that the surface reaction is the limiting reaction. So, therefore, all the other reaction rates really do not contribute. So, the key reaction which key rate which contributes to the overall reaction rate of this heterogeneous reaction is basically the surface reaction. So, we said that it is a surface reaction limiting. So, therefore, the rate of generation of toluene should actually be equal to the rate of the surface reaction, the rate at which the surface reaction is occurring, because it is the limiting step. And so, that will be given by K s into pH2, partial pressure of hydrogen, multiplied by the concentration of the sites in which the toluene is adsorbed, minus the concentration of benzene that is adsorbed to the catalyst surface, and then multiplied by the partial pressure of methane divided by the corresponding equilibrium constant. Okay. Now, this also means that the other reaction rates actually have to be 0. So, that also means that the R adsorption divided by the corresponding K h is approximately equal to 0, and also R desorption divided by the corresponding constant is also approximately 0. Okay. Now, from this we can actually deduce that the concentration of the benzene which is adsorbed to the vacant sites is actually equal to Kb Pb into Cb. Okay. Similarly, the concentration of the vacant sites, concentration of the sites on which toluene is adsorbed is actually given by Kt, Pt and Cv. So, this is actually obtained by setting R adsorption divided by Ka equal to 0. Okay, this is obtained by setting up this particular equivalence, by setting up R adsorption divided by Ka to be approximately 0. Now, in addition to this, the total number of sites in a given catalyst is approximately constant. Okay. So, we can now depict that by saying if Ct is the total number of sites in the catalyst, that should be equal to the total number of vacant sites plus the sites on which toluene is adsorbed plus the sites on which the benzene is adsorbed, because these are the two possible ones that can in principle be adsorbed onto the surface, because we assume that hydrogen is primarily in the gas phase and so is methane. So, therefore, C total should be equal to vacant sites plus the concentration of the sites in which the toluene is adsorbed plus the concentration of the sites on which benzene is adsorbed. Okay. So, by using this conservation property and also the expressions for the concentration of toluene adsorbed onto the catalyst side and the concentration of benzene adsorbed onto the catalyst side, we can find that the concentration of the vacant side is given by Ct divided by 1 plus Kb partial pressure of benzene plus Kt into partial pressure of toluene. So, if we know what is the rate limiting step, and if adsorption desorption processes in this particular case are not the rate limiting step, then we will be able to estimate the amount or concentration of the vacant site in terms of the observable quantities, that is the partial pressure of benzene, partial pressure of toluene, or the measurable quantities. Okay. So, now, once we know the concentration of the vacant site, we can now go back and try to estimate what is the overall rate at which the heterogeneous reaction is occurring. So, because surface reaction is the limiting reaction, so the reaction rate is now given by K s into C total divided by 1 plus K T P partial pressure of toluene plus K B P B multiplied by partial pressure of hydrogen K T P T minus K B Pb into Pm divided by Ks. Okay. So, this can be obtained simply by plugging in the expression for the vacant site catalyst concentration into the expression for the reaction rate, and we can obtain this particular expression. Okay. So, from here we can rewrite this as minus R t prime equal to K s C t. So, pull out K t from the expression divided by 1 plus K t E t plus K b into P b, that multiplied by partial pressure of H 2, partial pressure of toluene minus partial pressure of benzene, partial pressure of methane divided by another constant K p. Okay. So, this K p is nothing but the equilibrium constant of the surface reaction multiplied by the corresponding constants for the adsorption of toluene and the adsorption of benzene. Okay. Note that K p can be determined from the thermodynamic data of the overall reaction. Now, suppose if we neglect the reverse reaction, if we suppose we say that the total amount of the reaction primarily goes in the forward direction. So, if we neglect the reverse reaction, then we will see that the rate can actually be given by K s, which is the corresponding rate constant for the surface reaction, multiplied by C t, which is the total number of catalyst sites which is available in the catalyst, and K t, which is actually the corresponding constant, adsorption constant for toluene, and partial pressure of hydrogen, partial pressure of toluene, divided by 1 plus K b P b plus K t into P t. Okay. So, by clubbing in the K s, C t and K t into one constant, we can write this as K into partial pressure of H 2, partial pressure of toluene divided by 1 plus K b P b plus K t into P t. Okay. So, that can be written as this expression here, and so now we can actually rearrange this expression, and we can rewrite this as rearrange the expression as partial pressure of hydrogen, partial pressure of toluene divided by the corresponding rate should be equal to 1 by K plus K b P b divided by K plus K t P t divided by K. Okay. The final form of the rate expression is actually a linear equation. So, with this we have actually found the second step. So, remember that there are 4 steps here. First we deduce the rate law, and then we find the mechanism. So, what we have done is we have found the mechanism, and after we found the mechanism, we now need to go ahead and estimate the rate parameters. So, in order to estimate the rate parameters, it is useful to write in this, it is useful to write in the form of this rearranged expression, and you can see that there are 3 constants which are present. One is K, the other one is K b, another one is K t. So, now these 3 constants need to be estimated, and we will have to use the experimental data in order to estimate these constants. So, when we write the expression in this form here, then we will be able to use the experimental data, and we will be able to perform certain regression analysis in order to estimate these parameters. So, the rearranged equation can actually be written as A plus B into partial pressure of benzene plus C into partial pressure of toluene minus Z equal to 0, where Z is given by partial pressure of H 2, partial pressure of toluene divided by the rate which is measured experimentally, and A is given by 1 by K, and B is given by K b by K, and C is given by K t by K. So, once we have experimental data, which is presented in the experiments that have been measured. So, as can be seen from these experimental data. So, the partial pressure can be measured, the partial pressure of toluene, hydrogen, methane, benzene have all been measured, and different reaction rates have been measured under these conditions. So, using this data one can perform a regression analysis, and using the regression analysis one can find these constants A, B and C. So, use experimental data and one can perform a linear regression analysis. Linear regression analysis, and using the linear regression analysis we can now find these constants A, B and C. Okay. So, once we know these three constants, then we will be able to estimate what is the value of K, we will be able to estimate the value of Kb, and we will be able to estimate the value of Kt. And then we can find out by using the experimental data which was presented, the constants have been found, and from the data K will be equal to, for the data that is shown to you, the K will be equal to 6.18 into 10 power minus 4 moles per atmosphere square multiplied by kilogram catalyst per minute, and Kb, which is the corresponding equilibrium adsorption desorption constant for benzene, comes out to be 3.5760 atmosphere minus 1, and Kt turns out to be about 1.48 atmosphere minus 1. Okay. So, these are the constants that have been estimated from the experimental data using the rate law mechanism that we have just found out, and by performing a linear regression analysis on the experimental data. Okay. Now, what do we do with this data? Okay. So, what we can do is we can estimate some other information, we can deduce some other information in addition to these. For example, we can find out what is the ratio of the sites on which the toluene is adsorbed to the sites on which benzene is adsorbed. Okay. So, how do we do this? Because we have assumed that the surface reaction is a limiting step. So, the concentration of the adsorbed sites on which toluene is adsorbed is given by Cv multiplied by the corresponding equilibrium constant, adsorption desorption constant K toluene multiplied by the corresponding partial pressure. So, using that expression we can rewrite this as, by substituting those expressions we can rewrite this as Cv Kt into Pt divided by Cv Kb into Pb. So, that is given by, so therefore, cancelling the vacant sites we will see that this is equal to Kt into, if the total partial pressure at the inlet of the reactor is given by Pt naught, then Pt is given by Pt naught multiplied by 1 minus x, where x stands for the conversion of that particular reaction, okay, divided by Kb, which is the corresponding adsorption desorption constant, multiplied by Pt naught into x, and this is equal to Kt into 1 minus x divided by Kb into x. Okay. Suppose if the conversion x is about 0.25, that is, it is a 25% conversion, then we can plug in these numbers and we will see that this is equal to 1.48 divided by 3.57 multiplied by 0.75 divided by 0.25. Okay. So, this is approximately equal to 1.24. So, what this suggests is that the number of sites on which the toluene is adsorbed is actually about 25% more than the number of sites on which benzene is adsorbed for the given set of experimental conditions. Okay. So, that is an important piece of information that one can actually deduce. So, if one needs to have a 25% conversion or x to be 0.25, then the 25% of these sites has to be greater than the number of sites on which the toluene is adsorbed has to be greater than 25% greater than that of the number of sites on which the benzene is adsorbed. Okay. So, let us get back to the algorithm of designing a reactor. So, we looked at rate law, we looked at the mechanism, and by using the regression analysis, we found out what is the rate parameters, that is the parameters that is involved in the rate law. So, the next step is actually to design a reactor. So, let us consider a tubular reactor filled with catalyst. So, we get into the reactor design. So, let us consider a tube which is filled with catalyst, and if F T naught is the molar flow rate at which toluene is actually entering this particular reactor, and let us assume that F T is the molar flow rate at which the toluene leaves the reactor. Now, if I take a small element and if the total weight of catalyst which is packed till that location is W and the weight of catalyst packed at the other end of the element is W plus delta W, then we can write a simple mass balance in order to account for what is happening inside the reactor. So, the mass balance is what enters the element minus what leaves this element plus whatever is generated in this particular element, whatever is generated in this element should be equal to the amount of material that is being accumulated in that element. So, what enters that element? It is the F T, that is the molar flow rate of T at W, where the weight of the catalyst up to that point is W, minus the molar flow rate F T of toluene at W plus delta W, plus if the reaction rate is minus R T, then R T prime multiplied by delta W equal to 0. So, that is the rate law. Okay. So, where R T prime is the generation of the rate at which the toluene is being generated, and delta W is basically the amount of catalyst which is packed in that particular element. Okay. So, we can simply rewrite this as F T W plus delta W minus F T W equal to R T prime into delta W. Okay. And this can be rewritten as dF T divided by dW equal to R T prime. Okay. Now, F T can be written in terms of the conversion, that is equal to F T naught into 1 minus x. So, substituting the expression for the relationship between the molar flow rate of toluene and conversion, we can rewrite this as minus F T naught into dx by dW equal to R T prime. Okay. So, therefore, dx by dW equal to minus R T prime divided by F T naught. So, that is the performance equation. Now, by assuming that it is a plug flow reactor, by assuming that the reactor is a plug flow reactor. Now, moment we write the model equation for the reactor, we need to now plug in the rate law. So, we know that the rate law is given by K into the partial pressure of hydrogen, partial pressure of toluene divided by 1 plus Kb into partial pressure of benzene plus Kt into partial pressure of toluene. So, we can now plug in this rate law into the model equation, and then we will be able to estimate what is the how the conversion changes, how much toluene is actually being consumed inside the reactor. Okay. Now, in order to do that, we need to now express the partial pressures of toluene in terms of the conversion. So, we can do that. So, partial pressure of toluene is given by the concentration of toluene multiplied by R into T using an ideal gas law, and from stoichiometric relationship this can actually be expressed as C T naught into 1 minus x divided by 1 plus epsilon x into R t multiplied by P divided by P naught into T divided by T naught, where P naught is the total inlet pressure, and epsilon is basically given by y T naught into delta, where y T naught is the partial pressure of toluene at the inlet divided by the total pressure at the inlet, and delta is the change in the number of moles. And so, because in this particular reaction the number of moles is actually 0. So, therefore, this epsilon is equal to 0, which accounts for the change in the volume. And if we assume that it is isothermal, if we assume that the reaction is conducted under isothermal conditions, then T by T naught is equal to 1. Okay. So, now using these assumptions, we can now express the partial pressure of toluene in terms of the conversion as P T naught multiplied by 1 minus x into P by P naught. Okay. Now, P is essentially the pressure at that particular location, and so if I call that as y, so then you can write this as P T naught into 1 minus x into y, which is the ratio of the pressure at that location divided by the total inlet pressure. Okay. Now, similarly, we can write the partial pressure of hydrogen as P T naught multiplied by theta H 2 minus x into y, and partial pressure of benzene can be written as P T naught into x, where theta H 2 is the ratio of the concentration ratio of the amount of hydrogen which is present in the feed with respect to the amount of toluene which is present in the feed. So, in order to find the conversion profile as a function of the catalyst weight, we need to estimate this quantity y, which is the ratio of the local pressure with respect to the total pressure at the inlet. So, how do we find this? We can actually use the Ergun equation. We can use the Ergun equation in order to find this ratio, find this quantity y. So, the Ergun equation can actually be written as dy by dw equal to minus alpha by 2y into 1 plus epsilon x into T by T naught. Okay. So, what we have seen so far in this lecture is essentially how to use the experimental data in order to find out what is deduce the rate law which corresponds to the particular heterogeneous reaction, and then using that rate law and using the observations from the experiment to understand and deduce a mechanism by which that particular heterogeneous reaction perhaps occurs, and what is the rate limiting step in that particular series of in that particular heterogeneous reaction. Once we find this rate limiting step, then we can actually using the rate law, we can write the rate expressions for each of these steps, and by identifying the rate limiting step, we can find out what is the rate of reaction in terms of the observable or measurable quantities, and from that we will be able to use that rate law expression, find the rate law expression that we have derived in terms of the measurable quantities, and use the actual measurements and the reaction rate and plug it in, and using a regression analysis we can find out the rate constants and the other constants which is involved in the reaction rate law. Thank you.